Welcome to Dr. White's Fun with Graphs. In this video, we will start with just introductory material on definitions of graphs. So first we have a definition. A graph is a pair, an ordered pair V, E, where capital V is a set, which we consider the elements of this set to be the vertices of the graph, and E is another set of unordered pairs, which we call the set of edges. So this is a notation you don't find in the book called V choose 2. Given a set V, V choose 2 is the set of all subsets of V of size 2. So for instance, if V is 1, 2, 3, V choose 2 would have elements 1, 2, 1, 3, and 2, 3. Remember, these are unordered pairs, so order does not matter. 1, 2 is equal to 2, 1. So what is an example of a graph? Well, V is 1, 2, 3, 4, and the edge set is 1, 2 is an unordered pair, 2, 3 is an unordered pair, 3, 4 is an unordered pair, 1, 4 is an unordered pair, and 2, 4 is an unordered pair. We're going to write U is adjacent to V if U, V is an edge in E. And as notation, sometimes you see V of G written in place of V and E of G to be written in place of E. We sometimes write this because it's common to just write capital G for the graph without specifying the vertices and edges in advance. Another example that's quite common is G is the Facebook graph. And in that case, V would be all Facebook users. And U is adjacent to V if and only if U and V are friends. Of course, we commonly draw our graphs, so the notion of vertices and edges come from the way we used to draw these. The vertices are usually denoted with dots, and edges are usually denoted with line segments. So here's a drawing of our graph. Vertices 1, 2, 3, 4, and line segments connecting 1 to 2, 2 to 3, 3 to 4, 1 to 4, and 2 to 4. The reason why we define graphs explicitly in terms of set theory is because the important concept behind a graph is that it's defined in terms of these relationships and not in how we draw it. So you could also draw the graph this way or this way. But in all three of these drawings, the edge connections are all the same. So in some sense, these are the same graphs, even though the drawings are different. And so if you're actually interested in collections of objects and their relationships, you're interested in the graph. As another example, here is another graph. So you'll often see this done where we will define a graph by giving a drawing, and it's understood from the drawing what the edge set is. This graph has vertices 1, 2, 3, 4, edges 1 to 2, 2 to 3, 3 to 4, 1 to 4, and 1 to 3. This is a distinctly different graph because 2 is not adjacent to 4. So this does help us to see what the definition of equality should be. Two graphs are equal if they have the same vertex sets, and if they have the same vertex sets, the additional requirement that they have the exact same edge relationships. However, this example is kind of weird because if you just turn this drawing 90 degrees, the two graphs are the same. So if I just erase the vertex labels and rotated, you get the same picture. In that situation that we get the same picture is explained with this notion of graph isomorphism. So we say that two graphs, G and H, are isomorphic, or G is isomorphic to H, if there's a bijection, F, between the vertex sets. with the following feature. For any two vertices in the vertex set of G, U is adjacent to V in G if and only if their image is adjacent in H. In other words, every edge in G maps to an edge in H and vice versa. So these two graphs, this is G and this is H, they are isomorphic, and here's an example of the isomorphism. You send 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. You can check that edges involving numbers that are next to each other on the circle get sent to the corresponding numbers on the circle. In other words, this function just takes a number and increases it by 1, except that 4 gets sent to 1. So 1, 2 gets sent to 2, 3, 2, 3 gets sent to 3, 4, 3, 4 gets sent to 4, 1, and 1, 4 gets sent to 1, 2. And then 2, 4 does get sent to 1, 3. So edges are sent to edges correctly, and so this is an isomorphism. So with that in mind, once we talk about isomorphism, we eventually start getting used to drawing the graphs without actually labeling the vertex sets. I'm just saying up to isomorphism, this is the graph we're talking about. So now I want to talk about some special graphs. My first favorite sequence of special graphs are called the complete graphs. They're denoted K sub n. You might want to say it should be C sub n, but we're going to reserve C for a different collection of graphs. The K comes from a German word for complete. The vertex set is going to be the integers 1 to n, and the edge set is all the possible edges you can have. So here's K1, here's K2, here's K3, K4, and K5. In particular, a complete graph is any graph that's isomorphic to one of these. So you just have all possible edges. The next famous type of graph is called the path on n vertices. It has vertex set 0 through n minus 1, with every vertex I being adjacent to I plus 1, as I goes from 0 to n minus 2. So 0 is adjacent to 1, 1 is adjacent to 2, 2 is adjacent to 3, and so on. And so you get this. You can see why it is called a path, because it looks like a very, very simple straight path when you draw it this way. And again, up to isomorphism, a path graph is any graph that's is isomorphic to this graph. Finally, we have the cycle graph. This is the one we abbreviate with Cn. It also has the same vertex set as the path. Its edges are I is adjacent to I plus 1 modulo n. So you take the path graph and you just add an edge between the first and last vertex. So 0 is adjacent to 1 is adjacent to 2, but now we have 2 is adjacent to 0. 0 was adjacent to 1, which was adjacent to 2, which was adjacent to 3. We add an edge between 0 and 3. Of course, that's assuming that I tried to draw these things like this. But as you can tell, it's more common to actually draw them like vertices on a regular polygon. So now we have the notion of a subgraph. So given two graphs, G and H, if the vertex set of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G, then we say H is a subgraph of G. For instance, if G is this graph, and H is this graph, obtained by deleting the edge between A and B, and deleting the vertex E and all incident edges, then we see that H is a subgraph. So I described a way you can create subgraphs by deleting edges and vertices. Now, an induced subgraph is a special type of subgraph. It's one where the edge set in the subgraph is taken by taking all the possible edges you could have from W and intersecting it with the edges from G. In other words, take a subset S of the vertex set, like say ACE, and you're looking at all edges in G whose endpoints lie in that subset. So the only edges in that case is the edges between C and E. Then this is the induced subgraph. So the induced subgraph is found by only deleting vertices and incident edges to the vertices you've deleted. And so two examples of induced subgraphs are the notion of independent set and a clique. A clique is a induced subgraph that's isomorphic to a complete graph. So for instance, C, E, and D forms a clique of size 3, B, C, and E forms a clique of size 3. On the other extreme, an independent set would be a induced subgraph with no edges. So for instance, A and E form an independent set of size 2. And likewise, A and C forms an independent set of size 2, and D and B and D and A form independent sets of size 2. Harder to see is that there's no independent set of size 3, and that there's no clique of size 4 in this particular graph.